Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today, we are doing a really critical deep dive. We're looking at the nuclear force from Unit 13, nuclei. Our goal, as always, is to make this simple. So you really get the core idea and, are ready for any exam question.
Which is good because this is where everything we learned about electricity seems to just stop working. We spend so much time on Coulomb's law.
Exactly.
And then we get to the nucleus and it's like none of it applies.
You've hit on the perfect starting point, the fundamental paradox. So we have the nucleus. It's incredibly small. We're talking about, what, 10 to the power of minus 15 meters?
Femtometers. And it's packed. Just jam-packed with protons, all positively charged.
All positive. And like charges repel. So at that tiny, tiny distance, the repulsive force should be, it should be staggering.
It must be enormous. If you actually calculate it, the numbers are just astronomical.
They really are. So the big question, the one that puzzled everyone in the early 20th century was, simply, why doesn't the nucleus just explode?
Right. Why doesn't it just fly apart instantly? What could possibly be strong enough to hold it together?
It's easy to forget just how powerful this mystery force must be. Let's try to put it in perspective.
Okay.
If you take 1 kilogram of uranium and you fission it, you split it.
Right.
The energy you get is around 10 to the power of 14 joules.
10 to the 14. Okay, that's a huge number.
It is. Now, compare that. You take 1 kilogram of coal, you burn it. You get about 10 to the power of 7 joules.
Wait, 10 to the 7 versus 10 to the 14. That's a 10 million times difference.
Per atom, it works out to be 50 million times greater. That's the difference between a chemical reaction and a nuclear reaction.
Wow.
An enormous gap in energy. That's your proof. It tells you that the force holding the nucleus together, what we call the strong nuclear force, is on a completely different level than anything else.
So the fact that atoms even exist and are stable, that's the evidence that this force has to be real.
Precisely. And that brings us to the core idea. The nucleus is tiny, it's dense, it has almost all the atom's mass, and it only stays stable because this strong nuclear force is there, acting like the universe's most powerful glue. Let's try an analogy to really build a mental picture. Let's call it the crowded room analogy.
Okay, I'm listening.
Imagine the protons are people in a room who really, really dislike each other. That's their Coulomb repulsion. And
they're crammed into this impossibly tiny room, right?
Exactly. They're shoulder to shoulder. Now, you'd expect chaos, but there's a special rule in this room. An ultra-strong friendship force.
A friendship force?
Yes, and this force is so powerful that as long as they're practically touching, it forces them to stay together. It's an attractive force that completely overpowers their dislike for each other.
So the attraction wins, but only when they're super close. What happens if they move apart just a little bit?
That is the most important part. That is the whole trick. If they move even slightly apart, say more than a few femtometers, that friendship force, the nuclear force, just vanishes. It drops to zero.
And then all that's left is the original repulsion.
All that's left is the repulsion, and they would fly apart instantly. So the stability of the nucleus tells us two things. One, a new super strong force exists.
And two, that it must have an incredibly short range, unlike gravity, which goes on forever.
You've got it. Perfect. Now that we have the why, let's get a bit more technical. Let's see how we actually measure the strength of this nuclear glue. It all comes down to two ideas: mass defect and binding energy. Could you read out how NSERT defines them for us?
Of course. For mass defect, it says, the difference in mass of a nucleus and its constituents, P, is called the mass defect and is given by Z's MP plus AZ, NM.
Okay, and for binding energy?
And for that, it says, the energy required, EBC, is related to the mass defect by EB-MC.
Great. That's the formal exam-safe language. But let's break it down step by step. What it's basically saying is, if you take all the protons and neutrons of an atom and you weigh them separately, you get a certain total mass.
Okay, that makes sense.
But then, when you weigh the actual fully formed nucleus, its mass is always a little bit less.
So putting them together makes them lose mass. That feels very strange, like combining 4 1-kilo blocks and getting something that weighs 3.9 kilos.
Exactly. And that missing mass is what we call the mass defect, the AD. But it hasn't just vanished. This is where Einstein's famous equation comes in.
E equals mc squared.
E equals mc squared. That missing mass has been converted directly into the energy that's holding the nucleus together. That energy is the binding energy.
Oh, I see. So a bigger mass defect means more mass was converted into this this glue energy.
Yes.
Which means the nucleus is held together more tightly. It's more stable.
You understood it perfectly. More mass defect, more binding energy, more stability. But to compare apples to apples, especially for big nuclei, we look at binding energy per nucleon.
The average energy holding each particle in place.
Exactly. That's the true measure of stability. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Let's do a quick worked example to make this concrete. We'll use helium-4. It's a very stable nucleus. It has 2 protons and 2 neutrons.
Okay. The sum of the masses of 2 free protons and 2 free neutrons comes out to be 4.03188 atomic mass units, or U.
Right. But the measured mass of the actual helium-4 nucleus is only 4.00260 U.
So the mass defect, the M, is the difference, which is 0.02928 U. That's our missing mass.
Excellent. Now, we need to convert that mass into energy. We use a handy conversion factor. 1 U of mass is equivalent to 931.5 mega electron volts of energy.
Right. It's just a shortcut, so we don't have to deal with kilograms and joules and huge powers of 10.
Precisely. So we multiply our mass defect, 0.02928 U, by 931.5 me per U.
And that gives us about 27.3 MeV. That is a huge amount of energy for just 4 tiny particles.
It's phenomenal, isn't it? And if we divide that by the 4 nucleons, we get the binding energy per nucleon, which is about 6.8 MeV per nucleon. That confirms how tightly bound helium is. And this idea, this binding energy per nucleon, it connects directly to why we have nuclear power at all, to both fission and fusion.
Ah, the binding energy curve. I remember seeing that graph. It goes up, peaks, and then slowly comes down.
Exactly. And the peak of that curve, the most stable element in the universe, is iron-56. It has the highest binding energy per nucleon, about 8.8 MeV.
So everything in the universe wants to become iron.
In a nuclear sense, yes. Heavy things like uranium are on the downside of the curve. So when they split, that's fission, the pieces move up towards the iron peak, becoming more stable.
And they release the extra energy.
They release that mass difference as energy. And very light things like hydrogen are on the steep upslope. When they combine, that's fusion, they also move up toward the peak.
And release even more energy, because the slope is steeper there.
Precisely. The shape of that curve, which is dictated by the nuclear force, explains why both splitting big atoms and joining small atoms gives us energy.
Oh.
Okay, now for a very important section, the silent killers. These are the small misunderstandings that can cost you marks in an exam.
The things that seem right but are wrong.
Exactly. Misconception number 1. Students think the nuclear force is just a super strong version of the electromagnetic force.
I can see why. It's strong. It's in the nucleus. Seems logical.
It does, but it's completely wrong. The most crucial difference is that the strong nuclear force is charge independent.
Charge independent, meaning?
It acts equally between a proton and a proton and a neutron, and a neutron and a neutron. It doesn't care about charge at all.
Unlike the electric force, which only acts on the protons and ignores the neutrons completely.
Exactly. That's a fundamental difference. Okay. Misconception 2. People think the force is purely attractive.
But wait, if it was only attractive, wouldn't all the protons and neutrons just collapse into a single point?
Excellent question. And that's why we know it can't be purely attractive. The nuclear force actually has a repulsive core.
A repulsive core?
Yes. It's attractive in that sweet spot from about 0.8 to 3 femtometers. But if you try to push the nucleons closer than about 0.5 femtometers, the force becomes strongly repulsive. It pushes back.
Ah, so that's what keeps the nucleus from collapsing. It gives it its size and its density.
I got it. And our third misconception is about its range. We know it's short range, but students often miss the consequence of that. The property of saturation.
Saturation? What does that mean?
It means that because the force is so short-ranged, a nucleon only interacts with its immediate neighbors. It doesn't feel the pull of nucleons on the far side of a large nucleus.
So it gets saturated by the particles right next to it.
Yes. And this is why big nuclei don't just get more and more stable as they get bigger. It explains why the density of all nuclei is roughly the same.
I see. If the force were long range, uranium would be way more stable than iron because every particle would pull on every other particle. Saturation prevents that.
You've explained it better than I could. That's the key insight.
Yeah.
All right. To make sure all this sticks, let's use some memory anchors. For the nuclear force, you just need to remember the 4S rule.
The 4S rule. Okay.
It's short range, just a few femtometers. It's strong, about 100 times stronger than the electromagnetic repulsion it's fighting.
Short range, strong.
It saturates, only interacts with immediate neighbors. And it's the same for all nucleons, meaning it's charge independent.
Short range, strong, saturates, and same for all. Got it.
For a physical gesture, try this. Hold your hands close, almost touching. Feel that strong pull trying to keep them together. That's the strength.
Okay.
Now try to pull them apart. See how quickly that force disappears. That's the short range. Now try to push them through each other. You feel that resistance. That's the repulsive core we talked about.
That really helps visualize it. The magic zone is just that tiny space where the attraction is powerful.
Exactly. Remember that magic zone of 1 to 3 femtometers? Inside it, stability wins. Outside it, repulsion takes over. Okay, let's bring it all home. Here are 3 short, factual, exam-safe points to summarize the nuclear force. First, the nuclear force is essential to overcome the intense Coulomb repulsion between protons. It operates only at ultra-short ranges, being attractive from about 1 to 3 femtometers with a repulsive core below that.
Okay, that's point 1.
Second, we measure its strength using the mass defect. This missing mass is converted into the binding energy, with the binding energy per nucleon being the true measure of a nucleus's stability.
Got it. Mass defect becomes binding energy.
And finally, number 3. The unique properties of the nuclear force, like its short range and saturation, are what create the binding energy curve that peaks at iron 56. This peak is the fundamental reason why both fission of heavy nuclei and fusion of light nuclei release such massive amounts of energy.
So the force's properties explain all of nuclear energy.
In a nutshell, yes. To get maximum marks in 12 CBSE physics, chemistry, and maths, visit ProfSam.com.
That is ProfSam, right?
Yes, ProfSam.com. Thank you for joining us for this deep dive into the nucleus. Keep learning and keep asking those tough questions.